Good morning, everybody. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. Today, we are going to finish your Chapter 7 about the quantum theory and atomic structure. So today, we are going to be more focusing on the quantum number and associated orbitals. So we are going to also show you 4 different rules to allocate different electrons into the orbital in your atom. In other words, we are going to be more focusing on the quantum mechanical model of the atoms. Let's recall, how do we determine the different quantum numbers and what's the significance of those different quantum numbers and what are the allowed values, and then we show you some examples. The first quantum number is called the principal quantum number. You are going to use a smaller n to represent it. So this principal quantum number n represents the energy size, the magnitude of the energy. The allowed value will be n is 1, 2, 3, all the way to 7. Meaning the number of n is bigger, the related orbital energy will be higher. The second quantum number is called angular moment quantum number. You use a smaller l to denote it. Represents the shape of your orbital. So this value l can be ranging from 0 to n minus 1. n minus 1. This means your L number always one number smaller than n. For example, if your n is 3, your L can be at most equaling to 2. 3 minus 1. This L has different numbers, can have different number if you have one n. We are going to show you how to do this. The third one is called magnetic moment quantum number. You are going to use a smaller ml to represent it. This ml represents the orientations of your orbital, represents the spatial orientation of the associated orbital. The allowed value for your ml ranges from negative L to 0 to positive L. And the last one related to the electrons. The last quantum number called electron spin quantum number represents the direction of your electron rotation. This ms is going to be used to denote your electron spin quantum number. ms can be only either 1/2 or negative 1/2. Either positive or negative 1/2. So let's try to working out on the quantum number determination. Your n, always remember, must be positive integers. If n is number 1, your angular momentum quantum number can be only 1 minus 1, meaning 0. If your L is 0, your ML can be only 0. In this case, this orbital you call 1s, you only have one orientation for your 1s. If n is 2, n equals 2, your L can be ranging from 0 to 2 minus 1. From 0 to n minus 1, n is 2, so 2 minus 1 is 1. If L is 0, your ML can be only 0. If L is 1, your ML can be negative 1, 0, and positive 1. This orbital we call the 2s, 2p. If your n is 3, your L equals to 0, 1, and then 3 minus 1, which is 2. If L is 0, your ML can be only 0. If your L is 1, your ML can be -1, 0, and +1. Yes. If your L is 2, your ML can be -2, -1, 0, +1, +2. So those ones, those different numbers, so you have 1, 2, 3, 4, 5. These orientations, meaning you are going to have 5 different orientations if your L is 2. What's the name of these different orbitals? If L is 0, you call it S orbital. If L is 1, you call it P orbital. If L is 2, you call it D orbital. If L is 3, imagine you have 3, you call it F orbital. If L is number 4, you call it G orbital. So I believe we are also have a table to show you this. Let's practice how we are going to determine the quantum number for an energy level and how to determine the total number of orbitals which are allowed. Our problem is, what values of the angular momentum quantum number L and magnetic moment quantum number ML are allowed for a principal quantum number n of 3. Question 2. How many orbitals are allowed for this n equals 3? What's our plan? Our plan, point 1, you are going to determine this L value based on your n value. To restate, your L can take values from 0 to n-1. Again, smaller L, angular momentum quantum number L, always has one number smaller than n. Step 2. The values of your ML will follow the values of your L from -L to 0 to +L. Our solution. For n equals 3, allowed value of your L will be 0, 1, yes, and 2. 2 is calculated from 3 minus 1. If L is 0, your ML can be only 0. If L is 1, your ML can be -1, 0, and +1. If L is 2, your ML -2, -1, 0, +1, and +2. Totally, how many MLs are allowed? There is 1 over here, is 3, and this part 5. Totally 1 plus 4 plus 5 is 9 orbitals. This number of orbital can be calculated by n to the power 2. 3 to the power 2 is 9. In your homework, I gave you a little tougher question, which n is 4. How you are going to determine it? Meaning your L can be 3, 0, 1, 2, 3. Therefore, your ML will be more than -2 to +2. Your ML will be -3, -2, -1, 0, +1, +2, and +3. So totally, you are going to have 4 to the power 2, 16 different orbitals if your n is 4. So let's try to determine the name of your associated orbital. That orbital you also call subshell. So we want to determine the subshell name and the orbital quantum numbers. So our question is, given the name, magnetic quantum number, and the number of orbital for each subshell within the following quantum numbers. I'll give you 2 quantum numbers. Therefore, that orbital has a particular name. How do you determine the orbital name? So here is our plan. We are going to combine n value and the L designation to the name of your subshell. This L designation, you are not going to use the numbers. You are going to use the letter to represent it. And then if you know the L, we can find the ML and the number of orbitals. How do you do that? For that number of different orbitals, so I have another equation equals to 2L plus 1. We're going to show you a little later. And then what is the solution? So let's see. Question A. My N is 3, your L is 2. You put 3 first. And then this L, if it's 2, you call it D orbital. So therefore, you call it 3D orbital. 3D is the subshell name. So what's the possible ML value? If L is 2, your ML will be -2, -1, 0, +1, +2. So this is 5 different numbers. 5 different possibility of numbers, so meaning you have 5 orbitals. So you can calculate it by 2L plus 1. 2 times L, your L is 2. 2 times 2 plus 1 is 5. Our question B. Your N is 2, L is 0. If L is 0, you call the orbital S orbital. You place quantum number, principal quantum number N in front of this letter. So you call 2S orbital. So what's the possible ML value? Your ML only can be 0. Therefore, you only have one 2S orbital. This 2S orbital, you only have one orbital. Our question C. If your N is 5, L is 1, this orbital will be called 5P. Thank you. L is 1, you call it P orbital. If L equals 1, your ML ranges from -1, 0, and +1. Totally how many orbitals? Thank you, 3. 3 also equals to 2 times 1 plus 1. The last one, question D. If your N is 4, your L is 3. L is 3, you call it F orbital. You put 4 in front of F. 4 F orbitals, yes. So your L is 3. In your homework, you have this question. If your L is 3, your ML can be -3, -2, -1, 0, +1, +2, +3. Totally how many numbers you have? 7. This 7 can be calculated from 2, number 2 times 3 plus 1 equals 7. That's how you determine the different name of the subshells. Those subshells also called different orbitals. I also have some quantum numbers and the names, but I have some mistakes. This sample problem is asking our students to identify the incorrect quantum numbers. The problem is, what is wrong with each of the following quantum numbers designations and or subshell name? The quantum number designations, they are not right. The name of the subshell is not right either. A. If N is 1, your L is 1. Your ML is 0. And the name is 1P. Question B. N is 4, L is 3. ML +1. And you call it 4D. Your N is 3, your L is 1. Your ML -2, you call it 3P. Something wrong with this table. What's the problem? Our solution. Let's see. Your N, if it's 1, your L can be only, yes, 0. Your A, your L cannot be 1. So meaning this quantum number, angular momentum quantum number designation is not right. Your L can be only 0. So therefore this L orbital you call 1s. You never can have 1p orbital, doesn't exist. 1p orbital is not existing. Let's see our B. Number 4 and your L is 3, that's allowed. +1 is also allowed. If this is 3, your L is 3, what orbital you call it? 4F, thank you, 4F, not 4D. D d corresponding to L is 2. If L is 2, you call the d orbital. So our subshell should be F orbital. You call the 4F. How about this C? Yeah, this C, your ML cannot be negative 2. Your ML can be only -1, -2, -1, 0, and +1. So that's how you determine the ML value. So your L is 1, so your ML can be -1, 0, or +1, cannot be -2. So your orbital, you do call it 3p. So again, if your L is 0, you call it S orbital. If L is 1, you call it P orbital. If L is 2, you call it D orbital. L is 3, you call it F orbital. That's how you determine it. So this following, we have several slides showed you what the orbitals look like. Your 1s orbital look like a sphere. Your electrons occur along this region. If your orbital is 2s, you do have something we call a node, N-O-D-E. If your orbital is 3s, you have spheres, but you have 1, 2 different nodes. So that's how you determine the s orbital, p orbitals. So 2p, 3p, or 4p, different p orbitals, you have 3 different orientations. We call them px, py, and pz. So x, y, and z. This diagram A showed you the radical probability distribution of that electron clouds, the so-called wave function. And then this B showed the cross section of the electron cloud, which is depicted this way. What does that mean? Meaning the electrons occurs in the region of that yellow color. And then this figure C so showed the accurate probability contour. It's a contour. You did a simulation. Did you see something special? It's called the nodule planes. In that nodule planes, you are not going to find the number of electrons. Your electron does not occur in these nodule planes, only occur in this orange-colored spherical region. And the D showed a stylized probability contour. And then this E, so you have px, py, pz, totally 3 different p orbitals, put them together. And also I have your d orbitals. The A also is the radical probability distribution. B, cross-section of your electron cloud depiction. So it's more accurate. So px, dxy, dxz, dyz, and dx squared minus squared, dz squared. So that's the different shape of your d orbitals. Your f orbitals are also summarized in the solutions for one of your questions. This table 8.1 summarized the different quantum numbers and the associated electrons in the orbital. Also, the orbital names and the orbital shape, orbital numbers, and the totally quantum number of electrons in the associated orbital also listed in this table. Principal quantum number n, positive integers from 1 to 7 for now, represent the size of your orbital energy. Second one called angular momentum quantum number L is also the integers ranging from 0 to n-1. This one represents the orbital shape. If your L is 0, 1, 2, 3, corresponding to S, P, D, F orbitals. And also you have magnetic moment quantum number, integer from negative L to 0 to positive L. This quantum number representing the orbital orientation. The very last one represents electron spin quantum number MS. So only can be positive 1/2 or negative 1/2, represents the direction of your electron spins. And we also have 4 different rules which allow us to distribute the different electrons into the different orbitals. So your electrons in any atom can be described completely by a set of these 4 quantum numbers. So we call the quantum number set. A set of 4 quantum numbers, N, L, ML, and MS. The first 3 quantum numbers, N, L, ML, represent the orbital nature, describes the orbital of your atom. And the last one, MS, describes the electron spin. The first rule is called Alpha-Ball build-up principle. This Alpha-Ball build-up principle states that the electrons enter and fill in the lower orbital first, and then enter the higher energy orbitals. And then your Pauli exclusion principle, second principle, Pauli's exclusion principle, states that no 2 electrons in the same orbital can have the same 4 quantum numbers. Those quantum numbers, one of them must be different. In other words, the atom orbital can hold a maximum of 2 electrons. Every orbital can only be allocated or hold 2 electrons, and those 2 electrons must spin oppositely. The 2 electrons must have opposing spin. The third rule is called Hong's rule. Hong's rule states when several orbitals of equal energy are available, as in a given subshell, electrons enter with parallel spin. For example, you have px, let's say 2px, 2py, 2pz. If you have 3 electrons, you put the electrons into different orbitals, and then they spin in the same way. The last rule is called Madelung's rule. Madelung's rule is also called N plus L Aldrin rule. This rule states, the Madelung's rule states, the 4s orbital has lower energy than 3d orbital. You calculate the N plus L. 4s, 4 plus 1, which is 4 plus 0, s orbital L is 0, 4 plus 0, 4. 3 plus 2, d orbital L is 2, so that number 3 plus 2 is 5. 5 bigger than 4. Therefore, 4s orbital has lower energy than 3d orbital. So that gives the periodic table of the characteristic appearance. And also I re-summarized this Pauli exclusion rule and also Hong's rule, Alpha-Ball or build-up principle, and the Madelung's rule, also called N plus L Aldrin rule. That's all for today. Thank you so much. You have a wonderful day.